So in the course, we discussed the attention mechanism and we coded the attention mechanism from scratch last time. Here we will focus on the transformer implementation and we are going to use PyTorch built-in modules, and our focus will be on stable training of transformers. We will focus on a machine translation task on a small data set. Here I added an explanation. The focus will be on translating German to English. Like I said, the dataset is a small dataset compared to benchmark translation datasets like WMT that is used in the original transformer paper. We don't need to go for a very large transformer architecture, and we are using a scaled down transformer. The embedding dimension will be 128 compared to the original 512 in the paper by Vaswani et al. We are going to have only 4 heads, 2 layers in each encoder and decoders. The feed-forward dimension also, we have 500. Basically, it's 4 times wider than the model dimension. We'll have some dropouts too. So this will be a much smaller model, like I said, compared to the original paper. The positional encoding, we will go with the default. A review of multi-head self-attention. We will have this encoder that is purely self-attention. The decoder has self-attention, of course, with causal masking. We have to make sure we implement this correctly. There will be cross-attention. Decoder will use for its target token to attend to all of the source tokens. The position-wise feed-forward neural network is a 2-layer with ReLU. We have the normalization after each sublayer. So these are the hyperparameters for now. Of course, this can be improved. And the training loop is just what we did in the past. We will do the teacher forcing. And the forward pass is basically computing the prediction for the sequence, and the loss calculation is done with teacher forcing. The backward and the gradient clipping, we will have max grad norm of 1, and we will validate on the held out data, and we will compute the blue score. That is basically a measure of translation quality. Okay, so with that, let's get down to coding. So here are the imports and hyperparameters. The learning rate here, I choose a very small fixed learning rate for the ADAM optimizer. But as you will see, for a stable training, sometimes you need to have some form of scheduling, in particular warm-up scheduling. So there are examples like GNOME scheduler that involves warm-up and decay. There are a lot of nuances with that. I mean, of course, training transformers are maybe the most challenging part of it. Otherwise, everything else is parallelizable and very friendly with GPU and all of those goodies. But training really, sometimes we should be careful. So here, I don't have a lot of issues because of the small size and the rather simple data set. But for more challenging, larger architecture, the learning rate scheduling is very important. Okay, so we have this gradient clipping, and then we'll define the special tokens. Okay, so I'm going to set the seeds and then download the dataset. I will provide the code, and will be fast in this preamble parts. Okay, so I was trying to get a direct link for the dataset, but for some reason I couldn't. I'm going to just clone the repo, and I will describe the path as within this repo. So here's the code on how to handle this data set, alongside some very simple tokenization. For production level coding, we have to take on a better tokenization method, like for example, byte pair encoding, but here we'll go with very simple tokenization. Okay, so now that we have the NLP aspects aside and data is downloaded and tokenized, let's look at the model architecture. So first, let's take a look at this positional encoding. we basically fill out all of these positions for the max length of the sequence that we can encounter. We never get to 5,000, but let's just make it for because it doesn't hurt really. And then we will fill this up with the sine and cosine. So for now, let's just start with the indexing of the position. We are going to do a range from 0. We need this to be a float because I'm going to use it for calculating the encoding frequencies. The magic formula for calculating the frequencies is this. And now for the even and odd positions so even will get sine and odds will get cosine. So we have to be careful. For example, if D model is odd, we have to take care of that. But here, I mean, it's very rare to have an odd D model. So let's not do the transpose for now, and then let's register this encoding as a buffer. So basically it's saved, it will be saved with the model state, and we are not going to treat it like a trainable parameter. So the optimizer is not going to train this. Okay, so that's it, and let's write the forward. So what we did here is we basically add the positional encoding to the input tensor X, and we slice the encoding up to the actual sequence length of X. If you remember, we had this additional positions that is not necessary, so we only use as much as we want. Okay, so that's that. And let's write the transformer model class. Okay, so let's give some default values just to maybe simplify our life. I said 20, 128, and heads, we chose 4. We chose 4, and layers 2, the feed forward dimension 512, and dropout was 0.1. Okay, so that's that. And let's define a few things. Same for the decoder embedding. Okay, that's embedding, and let's do the positional encoding. And we are ready to define the structure of the one single encoder layer, right? So I'm going to use the native PyTorch function just for simplicity. We already did all of that coding of the attention from the scratch. So here we will focus on the training. So D model and heads, the feed forward, dimension, dropout, and here I want to add this batch first true, since our data may be a form of batch and sequence length and embedding dimension. So it doesn't hurt to have this. So we will set this to true. Okay, so that's that. And now we stack the layers using this. And then now we can look at the decoder stack. And as you see, we get all of these suggestions, which basically means how standard is this code. And that's pretty much for the stack of encoder and decoder. And now we can do the output projection for the generator of the tokens. I see the suggestion is pretty much what I want. Good. Let's just be more explicit here. Output projection. Okay, great. So now we need to initialize the parameters. And to do that, we have to write a function for it. But let's just put a placeholder for now. Init parameters, which we don't have yet, so we have to write it. So diff init parameters, which of course we know it's very important to initialize the parameters in a way that help in the stability of the training. For here, we are going to use Javier initialization to keep the variance of the outputs consistent across all of the layers. This prevents the signals from vanishing or exploding when they are propagating through the network. Okay, so for p in self.parameters, we basically do init Javier uniform, but it's always a good practice to say if p is more than a scalar, do that. Otherwise, it's not necessary. So Javier uniform is good. Okay, so what else we want? So we need to write a forward method, of course, and within the forward method, we have the formatter for that goes through the encoder and decoder. One thing that we need to before, so we need to write this forward method, of course, like I said, but for now, let's just go back here and we want causal mask because we need that in the forward. We need to basically we want to prevent the decoder from looking ahead and not cheat. So in PyTorch and Transformer, for any modules there, for positions that we want to be ignored or masked out, we will mark them as true or minus infinity. And let's do that. So generate a square subsequent mask, yes, and yep, we want to define a mask, which is an upper triangular, and the upper triangular elements gets 1. We also give 1 to diagonals, and we out a Boolean. Okay, so we set the diagonals also to 0 because we want to basically say everything up above the triangle, everything above the diagonal, we want it to be 1. And then later we get the Boolean, which returns true for them. So they will be masked, right? And then after that, we can return the mask. Okay, so now we can go ahead and write the forward method. We already have the causal mask, so we can use it. We don't need a source mask. So let's just write the target mask. Okay, so note that this is the length of the target. Maybe we can make it more explicit. And of course, the device. So this is basically the causal mask for the target sequence. And now let's work through the padding masks. Okay, so source padding mask. What we have here, let's just keep them as is for now. So basically we're telling the PyTorch to ignore the paddings here. Okay, so now we can do the embedding. So source, embed, and that's that. We have this positional encoding of the source and target. So in the original paper, the authors recommend scaling the embedding by the square root of t model. Let's do that too, just to stick with the original formulation. Okay, so that's that, and now we have the encoder that processes the source sentence. It only needs the source padding mask, so that's the output of the encoder. I'm going to call this memory, which is the sequence that we encode, the German sequence here. And now the output from the decoder that uses this target embedding takes in the encoder output or the memory and all of the masks that we made. So remember that this is the causal mask. Now we can return the projected output. So to evaluate the translation task, we can add a function that can compute the blue score. So in the past, we used the standard torch text, but that's deprecate. That's now is not used anymore. Here we can just implement this manually. I'm going to do this quickly, but I will provide the code for you. Oh, I see I made a mistake here. Let's go back. Yep. Oh, so let's give it a name to avoid that issue. See, we forgot a parenthesis here, here, and we're good. Okay, so here we have the blue score computation. Let's just separate them. I will add more commentation for you. Okay, that's that. And let's move on to some functions for the inference and the evaluation functions. Okay, so the inference or the translate here takes in the model, the source sentence, the source vocabulary, the target vocabulary, and the source tokenizer. Remember that. And we need some form of like max length. Okay, so this will be during inference, so model eval. And here we have to prepare the source tensor. which requires adding beginning of the sentence index and the indices of the sentence tokens. Plus, at the end, we have to add a end of sentence token for the source sentence. And then we need to convert it to a tensor and send it to the device. Okay, so source indices, first the BOS IDX. Let me see, source vocab, numericalize, source sentence, source tokenizer, plus end of sentence IDX, and then source tensor. Okay, so I went for more familiar version. For the target sequence, we just need the first token to start with, which is beginning of the sentence. It's like the initial point of generation of the sentence. So that's the target for now, and the model will populate that. Okay, so with torsionograd, and for the max length of the sentence, of course, it will stop when we encounter the end of sentence. So we need to have an if next token is EOS IDX, we have to stop this for loop. So the target, so let's just write it now. Why not? So if next token is end of sentence IDX, we want to break it. So let's go back here. Maybe we don't need that for now, we will write it. So output is that. Here it takes in the source and current target at this step. So this is basically the step of the autoregressive generation. So we have this TGT tensor, or the target tensor, that we will append to. Each time we will append the next token. Okay, so let's compute that next token, which is the output argmax, and that basically pops the item, and we append the next token to the target indices. Okay, we check if it is EOS. If it is EOS, stop the autoregressive generation. If not, continue doing this. And now we have to convert these indices back to tokens, because here the argmax looks at the probability distribution corresponding to each one of these indices and choose the one that is the maximum or the most probable. There's no creativity here in this translation job. It's a greedy decoding. We may get a better translation if we do a beam search, but let's just do the vanilla greedy decoding. And here we convert the indices to tokens. So we are decoding the sequence of the target token indices into the strings. To do that, we have to run it against the vocabulary of the target. And we have to skip the beginning of the sentence token and then look at each one of these indices to get the corresponding vocabulary. If we find it, good. If not, we will just assign an unknown token to it. So this is how we are doing it. So target vocab, index to string mapping, which is index to string mapping, get IDX, and if the index isn't found, return unknown. So we need to do this for all of these IDX in the target indices. We don't need to do it for the beginning of the sentence, so let's just skip that. And also we may need to remove the end of sentence if we encountered it here. Okay, so for that, we just check if the last token equals end of sentence. Okay, and we slice the last one. Good. Okay, so then we can return the target sequence, which we need to join all of these tokens. So to do that, it's enough to do this. To evaluate this sentence, this translated sentence, we will calculate the blue score. And it is important, of course, to do it in an autoregressive decoding way, just like the translation function. So no teacher forcing here. Otherwise, the evaluation will not be correct. So I will write the function here, and then we can move on to the training loop. Okay, so here I started with preparing the data set, first downloading the data, and then doing the tokenization and building the vocabulary. I'm going to only build vocabulary for those tokens that appear at least 2 times. So frequency threshold, we are setting it to 2. Then we can build this vocabulary. Same for the target. Okay, now we can set the dataset and data loader. Okay, so then the train loader and validation loader going to accept the suggestion, move on, and then we can initialize the model. So model transformer. Okay, let's see what we have. Number of heads, and then we have n layers, dimension of feed forward, and the dropout. That's it. We can send it to device. Looking good. And then what else we need? We need, let's print the number of parameters. It's always good. And then we will set the criterion, which is a cross entropy, which we need to ignore the padding indices. And then we can set up the add-on. So cross entropy loss that has to ignore padding indices. Now the optimizer, which is Adam. So torch optim Adam takes in the model parameters and the learning rate. Okay. So now we can write a for loop. Let me just track the best blue score seen so far during the forward loop, starting from 0 and then 4 epoch in range of if epochs. You already know this. I'm going to be fast. We'll skip most of this. Okay, so this within an epoch, we'll look at the batches of the sequences. During the training, we are doing teacher forcing, so the input to the decoder is a target sequence shifted right. So starting with BOS and then excludes the last token. So let's do that. So the target input and the expected output is the target sequence starting from the first real word. So we exclude the BOS. So target output, TGT. Okay, so let's zero the optimizer and do a forward. So the output is the model, source target, loss criterion. Okay, so here notice that I did some reshaping. The output was of this shape and we are converting it to batch times sequence and vocabulary size. And we also reshaped the target to be, so initially it is, here is batch and sequence. We are reshaping it to batch time sequence. So that's what we did, and that's the loss, and now we can do the backward. Here the gradient clipping, the optimizer step, we can do the validation of that epoch. For the evaluation, model eval loss for now 0. Let's compute this validation loss within the validation data. So with the torch no grad, we basically want to calculate the validation loss. We are going to use teacher forcing, and then we will compute the blue score. So blue score computation is a bit heavy. We only do it at the end of the epoch. And then we do some logging. We only save the model, the best model based on the blue score. So that's what I'm going to write. I will skip that to the most part. We'll add some codes for the logging of the during the epochs also. Let's do it here. Okay, so I think we have most of the things in place, and here we do a qualitative check for just a few sample sentences randomly generated, really. Okay, I did some error checking and now, oh, okay. It looks like things are working, so now we can activate our CUDA. We already get some interesting translation. The blue score is rather good here. I mean, 21 is good. Of course, the data set is easy. It's not very complex data. But we are on a good track, and maybe we can kill this training after blue score of around 30, 35. So another jump in blue score, 29, which I'm pretty happy with. And almost all of the translations are looking good. And yeah, so the training continues, but we can stop the video